You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Tokenization is the invisible first step in the journey from human language to machine understanding. When you type a sentence into a chatbot or prompt an AI system, it may feel as though the machine is directly grasping your words in their natural form. In reality, the raw characters are first converted into discrete units known as tokens. Tokenization is the process of deciding how to break a string of text into these smaller parts, whether they are entire words, fragments of words, or even single characters. Each token becomes a standardized input unit that the model can embed into numerical representations and pass through its layers. Without tokenization, the system would have no reliable way to interpret the messy and inconsistent stream of text humans produce. Thus, tokenization is not just a preparatory step, but the foundation upon which all later model processing rests. The reason tokens are essential is that models do not operate on raw text the way humans do. Instead, they handle sequences of integers, each corresponding to a token in a predefined vocabulary. This means the tokenizer effectively defines the universe of what the model sees. For example, if the tokenizer represents the word running as two tokens, run and ing, then the model perceives and learns those parts rather than a single unified whole. Similarly, unusual words may be split into smaller chunks, allowing the model to process them despite never having seen them exactly before. By shaping both input and output in this way, tokenization influences not only how models learn but also how they generate language. This hidden but crucial process dictates the efficiency, flexibility, and even fairness of the entire system. In the early years of natural language processing, tokenization was relatively simple. Word-level tokenization treated each distinct word as a separate unit. While intuitive, this approach quickly ran into problems. Languages are full of rare words, typos, and morphological variations, so a vocabulary built only from whole words ballooned in size and left models unable to handle new or misspelled terms. The alternative was character-level tokenization, which reduced the vocabulary to a manageable set of letters and symbols. While flexible, this method produced extremely long sequences and forced models to learn relationships at the character level, making training inefficient and slow. These early methods revealed the fundamental trade-off in tokenization, balancing the granularity of units against the efficiency and generalization of the model. The breakthrough came with the concept of subword tokenization. Instead of using entire words or single characters, systems began breaking text into subword units, small fragments that could be recombined to form any word. Subword tokenization strikes a balance between coverage and efficiency. Common words remain intact as single tokens, while rarer words are split into smaller chunks that the model can piece together. This approach ensures that vocabulary sizes remain manageable while maintaining the ability to handle words never seen during training. To return to our earlier analogy, it is like building with Lego bricks. You keep some larger pieces for efficiency but retain smaller pieces to ensure you can construct anything needed, even if it is novel or unusual. Subword methods thus became the standard in modern language models. One of the most widely used subword algorithms is byte-pair encoding, often abbreviated as BPE. Originally a data compression technique, BPE builds a vocabulary by iteratively merging the most frequent pairs of characters or subwords. At first, everything is represented as individual characters. Then the most common adjacent pairs are merged into single units, and the process continues until the desired vocabulary size is reached. The result is a set of subword tokens that efficiently capture both frequent words and reusable fragments. For example, running might be stored as run and ing, while international might be split into inter, nation, and al. BPE has the advantage of being simple, effective, and language agnostic, which explains why it underpins many widely deployed AI systems today. Sentence piece is another important tokenizer, designed with a different philosophy. Unlike earlier methods that assumed words were pre-segmented by spaces, sentence piece treats text as a raw sequence of characters, applying its algorithms directly, without relying on external preprocessing. This makes it especially powerful for languages without clear word boundaries, such as Japanese or Chinese. Sentence piece can implement BPE or a unigram model, and it outputs tokenized text as sequences of integer IDs ready for model input. By abstracting away assumptions about segmentation, sentence piece achieves language independence, making it an attractive choice for multilingual systems. Its design reflects the recognition that tokenization must work across diverse scripts and languages, not only alphabetic ones like English. Within sentence piece, the unigram model deserves special mention. Instead of merging pairs, it starts with a large vocabulary of possible subword units and then probabilistically selects those that maximize the likelihood of the training data. Less useful subwords are pruned away, leaving a compact but expressive vocabulary. This probabilistic approach allows multiple possible tokenizations of the same word, with the algorithm selecting the most likely one. The unigram model thus provides flexibility and often produces smoother vocabularies than BPE. It also allows for stochastic tokenization during training, where different segmentations can expose the model to varied perspectives of the same text. This subtle difference can improve generalization and robustness, demonstrating that tokenization is not just about efficiency, but also about learning quality. A key challenge in tokenization is handling the diversity of human language. Systems must account for Unicode characters, accented letters, and scripts ranging from Latin and Cyrillic to Arabic, Hindi, and Chinese. Poorly designed tokenizers may fragment words in languages with complex morphology or fail to represent rare characters consistently. The global nature of AI requires tokenizers that can flexibly and fairly process multilingual data, without privileging English or other high-resource languages at the expense of others. Unicode compatibility ensures that every possible symbol can be represented, while careful design avoids exploding the vocabulary size unnecessarily. Tokenization in this sense is not just a technical step, but also a cultural and fairness issue. The choice of vocabulary size embodies a classic trade-off. A larger vocabulary reduces the number of tokens needed to represent a sentence, since more words and subwords can be stored directly. However, this comes at the cost of a larger embedding matrix in the model, which increases memory and computational requirements. A smaller vocabulary keeps the embedding layer efficient but forces text into longer sequences, making inference slower and consuming more of the model's limited context window. Engineers must choose a balance depending on whether they prioritize efficiency of storage or efficiency of sequence processing. The decision influences not only computational performance, but also how gracefully the model handles rare words and novel phrases. Tokenization directly impacts model training because it defines the embedding layer, the sequence lengths, and the efficiency of data processing. If tokenization produces excessively long sequences, training becomes slower and more memory-intensive. If it produces inconsistent or poor quality tokens, the model learns weaker representations. Conversely, good tokenization compresses language into manageable units, making embeddings cleaner and context handling more efficient. It is not an exaggeration to say that tokenization shapes the very foundation of learning in language models, determining how well they represent meaning and how efficiently they scale to massive corpora. Training outcomes reflect not only model architecture but also the quality of tokenization choices made at the start. One of the major benefits of subword tokenization is its ability to handle rare or novel words gracefully. Traditional word-level tokenizers struggled whenever they encountered an unknown word, replacing it with an unknown token that signaled failure. Subword approaches solve this by breaking rare words into smaller, known fragments. For example, a model may never have seen the technical term neurogenomics, but if it knows neuro, geno, and mics, It can process the word by composing meaning from these parts. This flexibility is critical in real-world use, where new slang, jargon, and proper names constantly appear. By allowing models to construct novel words from familiar pieces, subword tokenization extends the effective vocabulary far beyond what is explicitly stored. Efficient tokenization also acts as a form of compression. By encoding frequent patterns into compact subwords, tokenization reduces the total number of tokens needed to represent text. This efficiency lowers storage requirements, speeds up training and inference, and reduces costs in systems where computation is billed per token. In this way, tokenization is not just a linguistic process but also an economic one, shaping the affordability of large-scale AI systems. Compression through tokenization mirrors the way human languages themselves evolve. Common phrases become shortened or merged over time to save effort, just as tokenizers merge frequent character pairs into efficient units. Evaluating tokenization quality is more challenging than it might appear. A tokenizer is not judged directly but through the performance of downstream tasks. If a model trained with one tokenizer consistently outperforms another across benchmarks, we infer that the tokenization was more effective. Multilingual models in particular highlight these differences. A tokenizer that segments one language efficiently but struggles with another can create uneven performance across linguistic groups. Researchers therefore test tokenizers by observing not only average accuracy but also fairness across diverse datasets. This underscores the fact that tokenization choices ripple outward, influencing not just internal efficiency but also real-world equity and usability. Despite advances, tokenization methods still have limitations. Handling whitespace, punctuation, and non-standard text such as emojis or internet slang remains a challenge. Over-segmentation can bloat sequence lengths, while under-segmentation can obscure meaning. In some cases, tokenization systems make arbitrary splits that do not align well with human intuition, leading to awkward representations. These limitations remind us that tokenization is an engineered approximation of linguistic structure, not a perfect reflection. Recognizing its imperfections helps practitioners interpret model behavior more carefully and motivates ongoing research into better tokenization strategies. Ultimately, tokenization defines the building blocks that attention mechanisms process in sequence. Every transformer model begins its work not with words as humans perceive them, but with streams of tokens determined by the tokenizer. Attention layers then decide how these tokens relate to one another, weaving them into coherent patterns of meaning. Without tokenization, attention would have no raw material to work on. This makes tokenization not merely a technical convenience, but an essential step in shaping how AI perceives and generates language. As we move forward, understanding this hidden layer prepares us to appreciate the mechanics of attention, the next major concept in our journey through advanced AI. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Cross-language tokenization issues reveal just how uneven the efficiency of current systems can be. In English, a relatively analytic language with many short words and spaces between them, tokenization schemes often produce concise sequences. But in languages like Finnish or Turkish, where long compound words are common, or in logographic languages like Chinese and Japanese, where characters themselves carry complex meaning, tokenization often results in a greater number of tokens per sentence. For example, a single German compound noun might be broken into many tokens, whereas its English equivalent is split across shorter words. This means that the same idea expressed in different languages can require very different token budgets. In practice, this inefficiency translates to higher costs, longer sequences, and less effective use of context windows for certain languages, creating subtle disadvantages that ripple through model performance and accessibility. These disparities connect directly to fairness considerations in tokenization. If a language consistently produces more tokens for the same semantic content, its speakers are, in effect, paying more for the same level of AI service, especially in usage-based pricing models. Moreover, models trained with uneven tokenization distributions may perform better on efficiently tokenized languages and worse on those that produce longer sequences. This asymmetry can reinforce existing inequalities in digital access and representation, privileging languages like English while marginalizing others. Tokenization fairness is therefore not just a technical detail but a question of linguistic equity. Addressing it requires deliberate research and design choices to ensure that multilingual systems do not inadvertently disadvantage entire populations because of how their words are segmented. Tokenization is not limited to text. In multimodal systems where models handle images, audio, or video, equivalent processes exist to create token-like units. For images, pixels are grouped into patches, each treated as a token-like representation of a region. In audio, spectrograms are segmented into slices that serve as tokens for sound. These multimodal tokens feed into models much like word tokens, allowing transformers to process non-textual data in sequence. Understanding this parallel reveals that tokenization is not just a linguistic trick, but a universal mechanism for converting raw sensory input into standardized, discrete units that models can handle. By extending the concept across modalities, researchers have unified the way AI systems represent and process very different kinds of information, paving the way for true multimodal intelligence. When tokenization is applied to programming languages, unique challenges arise. Code is not free-flowing like natural language, but governed by strict syntax, symbols, and structures. Tokenizers for code must recognize operators, keywords, variable names, and punctuation with high precision, since errors in segmentation can alter meaning entirely. For instance, equals as a comparison operator must be recognized as a single unit, not two equals signs. Similarly, the difference between as's and carries structural significance that cannot be overlooked. Tokenization for code is therefore less about linguistic efficiency and more about preserving syntactic accuracy. Specialized tokenizers, sometimes designed in collaboration with compilers, have emerged to handle programming languages effectively. This shows that tokenization adapts to the unique properties of each domain, reflecting both its flexibility and its critical importance in ensuring model reliability. Another major implication of tokenization is its impact on context windows, the fixed-length buffers that determine how much input a model can process at once. Since context windows are measured in tokens, the efficiency of tokenization directly affects how much actual text can fit. If a tokenizer segments text into many small tokens, the context window fills up quickly, limiting the amount of information available to the model. Conversely, efficient tokenization allows more content to fit within the same window. This has practical consequences for everything from document summarization to long-form conversations. In short, tokenization choices shape not just performance, but also usability, influencing whether a system feels capable of handling complex, extended interactions, or struggles with truncation and loss of context. Because many AI services are priced based on token usage, tokenization also directly affects cost in model APIs. Every input and output token consumes resources, and fees are calculated accordingly. Inefficient tokenization means higher costs for users and organizations, even when the semantic content is identical. For businesses deploying AI at scale, these costs accumulate into significant expenses. Tokenization design thus becomes an economic decision as well as a technical one, with direct financial implications. Engineers and decision-makers alike must pay attention to how tokenization shapes not only model accuracy, but also the affordability and scalability of AI services. This economic angle reinforces the hidden power of tokenization in shaping the viability of AI adoption. Backward compatibility issues arise when tokenization schemes are updated midstream. If a model is trained with one tokenizer and later switched to another, inconsistencies appear between training and deployment. Words once represented as one token may suddenly become multiple, altering sequence lengths and embeddings. These shifts can degrade performance or break existing applications. For organizations deploying AI, this creates a dilemma. Stick with an outdated tokenizer to preserve continuity, or migrate to a better one at the cost of retraining and retooling. This problem highlights how deeply embedded tokenization is in the infrastructure of AI systems, and how seemingly small changes ripple outward into engineering, economics, and user experience. To address some of these limitations, researchers are experimenting with adaptive tokenization methods. Instead of using a fixed vocabulary and segmentation strategy, adaptive tokenizers dynamically adjust based on input characteristics. For example, they may use longer subwords for common words and shorter fragments for rare or technical terms. Some research even explores context-sensitive tokenization, where the segmentation changes depending on surrounding words. These adaptive methods promise greater efficiency and fairness, but they also introduce complexity in implementation and training. Still, they signal an important frontier, suggesting that tokenization does not need to remain static, but can evolve alongside advances in model design. The risks of over-segmentation demonstrate one of the core challenges in tokenizer design. If text is broken into units that are too fine-grained, sequences become unnecessarily long. This slows inference, consumes more memory, and limits the effective use of context windows. For example, splitting international into 6 separate tokens instead of 3 increases sequence length without adding real value. Over-segmentation also burdens users with higher token costs in API models. In short, breaking language into too many pieces fragments meaning and inflates expense, demonstrating the importance of careful calibration in tokenizer design. Under-segmentation, however, carries its own risks. If tokens are too coarse, the model loses flexibility in handling novel or compound words. Imagine if internationalization were represented as a single token. A model encountering a similar but novel word, like regionalization, would struggle, since it cannot break the word into smaller parts to reuse. Overly coarse segmentation reduces generalization, forcing models to memorize rather than recombine. The balance between too many and too few tokens is therefore delicate, and finding the sweet spot is central to effective tokenizer design. These cases illustrate why tokenization is not a trivial pre-processing choice, but a critical driver of downstream performance. Interestingly, emergent abilities in large models may depend in part on tokenization efficiency. If tokens align well with meaningful units of language, models can leverage them to produce more coherent generalizations and unexpected skills. Conversely, poorly segmented tokens may obscure patterns and limit the potential for emergent behaviors. Researchers studying scaling and emergence, therefore, often consider tokenization as a hidden factor shaping results. In this way, tokenization is not just a support function but an active contributor to the kinds of intelligence models can exhibit at scale. It determines the building blocks from which surprising and powerful behaviors can arise. To evaluate tokenizers systematically, researchers often rely on downstream benchmarks. Instead of judging tokenization in isolation, they assess how models trained with different tokenizers perform on tasks like translation, summarization, or question answering. Benchmarks reveal whether one segmentation strategy produces stronger representations, better generalization, or improved efficiency. In multilingual settings, benchmarks also expose fairness issues by showing performance disparities across languages. Evaluation through tasks ensures that tokenization is judged by its real-world impact, not abstract theory. This pragmatic approach underscores how tokenization sits at the heart of AI performance. Tokenization also carries implications for bias. The way words are segmented can encode cultural assumptions or emphasize certain linguistic traditions over others. For example, tokenizing gendered forms differently in some languages could reinforce stereotypes, while uneven handling of regional spellings might privilege dominant dialects. Bias can creep in not only through training data, but also through the foundational choices in how that data is represented. Recognizing tokenization as a potential vector for bias forces researchers to approach it with ethical care, ensuring that segmentation does not inadvertently perpetuate cultural or linguistic inequities. From an industrial perspective, tokenization is a high-stakes decision. Companies training and deploying AI systems carefully evaluate whether to use BPE, sentence piece, or custom tokenizers tailored to their domain. The choice affects model size, training efficiency, inference cost, and user experience. For example, a company focusing on multilingual chatbots may prefer sentence piece for its language independence, while one focused on code generation may design specialized tokenizers to capture programming syntax. These decisions ripple outward into economic models, customer satisfaction, and competitive advantage. In this way, tokenization decisions become strategic, influencing not just engineering but the business trajectory of AI organizations. Ultimately, tokenization serves as the gateway to attention mechanisms. Once text is broken into tokens, attention layers decide which tokens matter in context and how they relate to one another. Without tokenization, attention has no sequence to process. Without attention, tokens remain isolated fragments. Together, these mechanisms form the backbone of modern language models. Understanding tokenization prepares us to explore attention with greater clarity, recognizing that the quality of the building blocks shapes the strength of the structures built upon them. This transition from tokenization to attention is both technical and conceptual, moving us from the smallest units of input to the larger webs of meaning they form. In conclusion, tokenization is the hidden but essential layer that converts raw language into the units models use to think. It shapes efficiency, fairness, and performance across languages, domains, and modalities. From BPE and sentence piece to emerging adaptive methods, tokenization strategies influence costs, context windows, and emergent abilities. They even encode cultural and ethical implications, making them more than a technical curiosity. By seeing tokenization clearly, we recognize its role as the quiet architect of model intelligence, shaping how language is represented and understood. With this foundation in place, we are ready to examine attention, the mechanism that determines how tokens interact, and which pieces of information rise to the forefront of model reasoning. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.